In this video, we're going to explore forming potassium solid using the equilibrium of electron transfer. So one of the industrial means of forming potassium is that you get a big container of KCl solid and some sodium metal. You seal it up, pull a vacuum, and have what's called a cold finger. You have a cooling component up above this mixture because the bottom's going to get pretty dang hot. Well, sodium solid has a boiling point equal to 1150 Kelvin. Its melting point is far below that. Potassium has a boiling point equal to 1032 Kelvin. Why this is important is that potassium chloride, the ionic material, has a melting point equal to 1043 Kelvin. This means that you can melt potassium chloride salt before you've boiled away your sodium. Now the sodium will turn molten, but it won't boil till a good 100 degrees Kelvin above the melting point of your potassium chloride. However, your potassium metal, if you had any, would boil at this temperature. Why that matters? Well, let's explore this reaction for a minute. Sodium is capable of becoming sodium plus and an electron. There's an E naught for this at 2.71 volts. Sodium's really good at giving away its electron. Potassium, on the other hand, has an E naught equal to negative 2.93 volts. So if we imagine just flipping this sodium reaction around for a moment, well, that would become a minus 2.71 volts. Between sodium and potassium, sodium's higher on the periodic table. It's more electronegative than potassium. We see that in its potential. It's slightly more positive, well, or at least less negative than potassium, 2.7 versus 2.9. That sodium wants that electron more. So if we tried to do a reaction where a sodium metal gave its electron to a potassium to become potassium metal and a sodium, well, that would be our bottom one here and the flipped top one. So that'd be negative 2.93 volts plus positive 2.71 volts for a negative 0.22 volts. That's non-spontaneous. Sodium does not want to give potassium its electron. But that's not a huge voltage difference, which means in the equilibrium, as all these ions are melted and bouncing around and bumping into each other, there is some small number of occasions that a sodium will transfer its electron to a potassium. Now, while it's a salt and an ion, potassium might melt at 1043, but it's certainly not, potassium plus is not vaporizing. It's definitely not the boiling point of potassium chloride. But at any given instant where one of them happens to acquire an electron for that tiny little brief moment of time that the equilibrium says some of them should have them, should that potassium happen to be at the surface, well, it's hot enough to boil. That potassium can drift away. And then it sticks to the cold finger, because the cold finger is cold enough to bring it back down to solidification temperatures. And bit by bit, potassium will stick to the cold finger. And over time, we will build up a crystal of potassium dangling on that cold finger. This is one of the actual methods to purify potassium. You take potassium chloride salt, sodium metal, you heat them both up to just over the melting point of potassium chloride, but not yet to the boiling point of sodium, so that when you have these small electron transfers, potassium can break free. How viable is this? If this is a 1 in a billion relative ratio, it's not going to happen very quickly. Electron transfers can happen pretty quick, but it still needs enough of them at the surface often enough to escape to make this a feasible method. So let's solve that. Given the info above, let's find K of equilibrium for this transfer. And we're going to assume we can use standard state values. That is a little unreasonable here, as standard state's 298 Kelvin, and we're up in the 1040 some Kelvin. But for our purposes, it's going to help us see roughly where we're looking at in terms of equilibrium constants. So go ahead and pause. Try to use this info to solve the equilibrium constant for this reaction. How favorable is it to put that electron on potassium versus sodium? And then come on back. Well, if you're back, we have the voltage difference. Remember that our E cell was equal to 0.0592 volts per electron transferred in the reaction, log of K. Well, they're both column 1. They're both 1 electron transfer, so N is just 1. So what we really have is our negative 0.22 volts is equal to 0.0592 volts log of the equilibrium constant. We can divide our 0.0592 volts across. We'll find that the log of our equilibrium constant is equal to 3.7162 negative. Take the 10 to both sides. We'll find that our K value is equal to 0.000192. So not particularly favorable. About 2/10,000ths as much potassium as sodium. However, 2 in every 10,000 or so will transfer. So a little bit at any given moment of the potassiums should have an electron. In a large container, that's going to give you enough potassiums that as they break free, well, now that potassium with electron is gone, another sodium is likely to give it up to balance the equilibrium. Every time a potassium leaves, we disturb the equilibrium value, favoring sodium giving another electron to potassium. And so bit by bit, we can transfer all of those electrons over, capture a nice crystal of potassium. And so while not the largest K by any means, it's not an unreasonably small one. 2 times 10 to the minus 4 is not a terribly tiny equilibrium constant. There is enough favorability that this can be done at an industrial reasonable speed.